Okay, welcome back. You've made it this far. The previous video, we used Kirchhoff's laws for this combinational circuit up here to create three equations for our three unknown currents. Two of them come from Kirchhoff's voltage law, and the third one here comes from Kirchhoff's current law. We're going to rewrite this in matrix form. We have three things on the left side of the equation: 36 volts, 36 volts, and 0. Our three unknowns in order from left to right is I1, I2, and I3. As you can see here, I have 1, 2, 3, 4, 5, 6, 7, 8, 9 coefficients being multiplied by these unknowns. I have a 12 ohm multiplied by I1, 15 ohms multiplied by I2, and 0 multiplied by I3. So this row and this column represent my first equation. My second row will be 12, 0, 10. And my final row will be negative 1, 1, 1. And we get a really interesting thing here with the matrices. If you look at the units inside the matrices, all the units on this matrix are in volts. So I'm going to call that matrix V. And all of my units in this matrix are in ohms. I'm going to call that matrix R. And my unknown matrix is I. And voila, we got Ohm's law in matrix form. Isn't that fascinating? How Kirchhoff's laws are really just a complex version of Ohm's law and more generic, and that they are in matrices. All right, so how do I solve this then? So I'm going to rewrite it again. I had a matrix V equals a matrix R times a matrix I. I'm solving for matrix I. Now, if this was a normal algebra equation, you would be like, hey, divide by R. But there's no such thing as dividing a matrix. However, there is such a thing, in a way, as an inverse matrix, which is not written 1 over R. It's written as R negative 1. So pay attention to this. What I'm going to do is I'm going to multiply the inverse matrix to the left side of the matrices. R negative 1 times V, R negative 1 times R, and my unknown I. And it's important because there is a thing about matrices is that multiplying a matrix on the left is different than multiplying it on the right. I had to multiply the R negative 1 to the left sides of my original equation because by definition, R negative 1 times R should give me what's known as the identity matrix in like multiplying by 1. So now I have R negative 1 times V equals my unknown I. I'm going to use Desmos calculators for matrices to do this. Okay, so let's define the matrices. Unfortunately, V, I, and R are not options, so I'm going to have to go with this. So let me define my voltage matrix by saying new matrix, which is going to call it to A. It was a 1-column, 3-row matrix. According to my notes, it was 36. 36, and 0. I'm going to press enter. Now I have inputted into the system, I have a matrix A. For my resistance matrix, I'm going to use B. New matrix. I have 3 rows and 3 columns. I had 12 ohms, 15 ohms, 0. I had 12, 0, and 10. And then I have my Kirchhoff rule of current that gave me -1, 1, and 1. I'm going to hit enter. Now, according to my notes, what I have to do is multiply the inverse matrix of the resistance by the voltage one. In other words, I have to take matrix B and take its inverse and multiply it by matrix A, and voila, it gave me the answer I was looking for. 2.8 and 1.2. Now let's check to make sure that that makes sense. So it says current 1 is 2 amps, current 2 is 0.8 amps, and current 3 is 1.2 amps. That was the result. If I redraw that on my circuit, first of all, I notice that Kirchhoff's current law was obeyed. 2 amps came into the junction, and 0.8 went down this path, and 1.2 amps went down that path. Makes more sense that less amps decided to go down this path because there is more resistance on that path. So less current went down that path. Let's check the voltage drops. Remember, we have 36 volts here. So the first voltage drop is going to be 10 times 2. So that's going to drop 20 volts. The next one is 0.8 times 15. I'm going to do that in my calculator, 0.8 times 15. And that's a voltage drop of 12 volts. This one is a voltage drop of 2 times 2, 4 volts. Let's check this loop. 20 plus 12 is 32. 32 plus 4 is 36. And as we can see, for loop 1, 36 minus 36 gives us 0. It is perfectly fine. Over here, for these voltage drops, I'm going to have a 5 times 1.2, which is 6. I have that again. I have 2 6-volt drops for each resistor. Hey, by the way, notice how 6 plus 6 is 12, because this path is parallel to this path, and parallel paths always have the same voltage. So the voltage drop from here to here is a total of 12 volts. So yes, it made sense, and we got our answer. Thank you very much. That's the conclusion of combinational circuits using matrices and Kirchhoff's laws.